So you have a linear activation function, then threshold activation function, you have sigmoid activation function, then logistic activation function, tanh, which is also called as hyperbolic tangent, ReLU, leaky ReLU, parametric ReLU, and Gaussian softmax. So these things we have covered in last class. Now let us solve one problem. I hope this is not covered in earlier videos. Find the region in x1, x2 plane where neural network output is +1. Okay, where neural network output is +1. And you have been provided a network like this. So there are two layers in this network. So layer number 1 is here. Okay, and layer number 2 is this side. So in layer number 2 there is only one neuron. So this is one neuron, and in layer number 1 there are, I think, 4 neurons. If you see input of layer number 1, you will find there are two variables, x1 and x2, and one thresholding terminal, or a fixed terminal which is connected to -1. So what is input to this network is, suppose y is equal to x1, x2 and -1. So this will be my input. Now what is question? Question is, find region in x1, x2 plane where neural network produces +1. So suppose I take a plane, I think I should take here, say this is x1 and this is x2. So if I take any point here on this x1, x2 sheet, suppose this is the point, say let us say A, then it can be defined with the help of two numbers, that is x1 and x2. Now our task is to find out for this point A whether I am going to get +1 or not. So if I am going to get +1, I will be in interest of that point. Now I can move this point A anywhere in this space, and I want to find out which part of this sheet produces +1. Okay, or if I keep this point A on this plane, suppose I put it here, whether this point will be producing +1 or not. So that is what is our question is. So it means actually it's a two-class problem. Say one is representing, suppose, class 1, and the other 0 or -1 is representing the class 2. Then we want to find out which region of x1, x2 sheet or plane belongs to class 1 and say class 2. So class 1 is represented by +1 response. So that is what this question is. Okay, is this covered earlier? Anybody can respond?
No, sir.
Yes or no?
No, sir.
Okay. So thanks for your response. I want those responses frequently so that our class will be interactive. Okay. Now how to find out this? So let us find out what these neurons are doing in this problem. Suppose I take neuron number 1, what it is receiving, you can see here it is receiving x1, multiplied by 1, and it is receiving this -1 multiplied by 1. So summation of these two is carried out here, and that is given to a threshold unit. Similarly, you can see other connections for neuron 2, you can find out for neuron 3, you can find out for this fourth one. And output of these 4 neurons is passed on to a next neuron. Okay, this is neuron 5. Now, what is our, say, input? Let us start from, say, backside. Say if I start with this neuron, what it is receiving. So these are O1, O2, O3 and O4. These are inputs to this last neuron. So this last neuron net value, suppose I call it as net 5. So this will be equal to this O1, this one multiplied by its importance 1, that is it will be O1, then O2, then added with O3, and then finally O4. There is one more terminal here which is fixed to -1, and its importance is 3.5. So -1 multiplied by 3.5, so that will be -3.5. So this is my total net. Okay. Now suppose this threshold logic unit is implementing this kind of activation function, which is producing +1 whenever your net value is, let us say, greater than equal to 0. Okay. So whenever this total sum of 4 neurons is more than 3.5, then and then it will produce +1. You got my point? To fire this last neuron, what is condition? When it will be getting fired? Whenever this net 5 is greater than 0. Now when this can happen? Say whenever O1 is equal to 1, O2 is equal to 1, O3 is equal to 1, O4 is equal to 1. So when all neurons, previous neurons are fired, you will get 1 here, 1 here, 1 here and 1 here. And from that 4 ones, so total will be 4, 3.5 will be subtracted because this is my fixed connection or a bias connection, which is comparing net value with respect to 3.5. Now if this total is greater than 0, then and then only this last neuron is fired. So that is what our condition is. So I am talking about this because this is the required condition in your problem. What is your task? Your task is to find out when this last neuron produces +1. Okay. So what condition we have obtained? We have obtained that, or we have observed that when neurons in layer number 1, if all of them are fired, then and then only this is going to fire. So that is our condition. So I can write even here that O1 plus O2 plus O3 plus O4. If this is greater than 0, then minus, sorry, not 0. If I take this 3.5 this side, I should write greater than 3.5, then say neuron 5 is fired. Okay, this is the condition that we have observed. Now we have to go individually what these previous neurons are doing. That means I want to find out now when this neuron number 1 will produce plus 1, when this 2 will produce plus 1. Okay, so let us take now neuron number 1. So what it is implementing? It is implementing x1 multiplied by 1. So x1 multiplied by 1, then this minus 1, okay, multiplied by this plus 1. So this is minus 1. So this is what the net value of neuron number 1. Now you can see when this neuron is fired, our activation function is same. So activation function is same for all these 5 neurons. So this is net value, this is 0, and this is output. So you can see whenever my input is, that is for neuron number 1, what is input now? It is just only x1. So whenever x1 is greater than 1, this first neuron gets fired. So meanwhile, in your chat box, you will type your registration numbers. Okay. So whenever x1, so this implies that whenever x1 is greater than or equal to 1, I am going to get plus 1 for neuron number 1. Okay. So if I go to the plot, if I go to the x1, x2 plot, I can draw here, suppose like this, some graph of x1 and x2. What is implemented by neuron number 1 is that this is the line x1 equal to 1. So you must be greater than 1. So this is my 1, this is 0. So whenever your input is this side of this line, okay, whenever your x1 belongs to this side of the line, your neuron number 1 is going to fire. Okay, so keep in mind that neuron number 1 will fire whenever your input x1 is more than this line. Anybody from say this point onwards will fire neuron number 1. Now you go to the second neuron, what it is doing. So second neuron, say neuron number 2. What is its net value? The net 2 is equal to, you can just observe, say x1 multiplied by minus 1. So it is minus x1. Then this minus 1 multiplied by minus 2. So it is plus 2. Okay. Now this is my net value for second neuron. Now can you think when this second neuron will fire? Can anybody say about this? When this second neuron will fire? So whenever
X1
you are
less than 2.
yes,
X1 less than 2.
right, absolutely right. So whenever x1 is less than 2, this second guy is going to fire. Suppose I write here 2, then implementation of this second neuron is this particular line. So what it is saying, this neuron number 2 is saying, if you want me to fire, be this side of this line. Okay, what neuron number 1 is saying, you should be ahead of me. So if I combine this, say, regions of these two neurons, then they are deciding this particular zone of this x1 x2 plane where both will fire at a time. So if I choose a point, say A here, then both are going to fire. Similarly, try to observe now what neuron number 3 is doing. Suppose I take neuron 3. What neuron 3 is doing? So its net value is net 3. It is receiving only x2 multiplied by 1. So it is x2 only. There is no x1 here. So whenever x2 is positive, this is going to fire. So this implies that x2 must be greater than 0, then this will produce +1. So where is that region? So that region is nothing but this x1 coordinate. So you must be above this. Okay, so you must be above this. So this is my neuron number 3's job. I repeat, what is job of neuron number 1? Neuron number 1 says, go this side. What is job of neuron number 2? Says, go this side. And now what neuron number 3 is saying, go above me. Like this. So go above this x2 equal to 0 line. That means, if you want to fire 3 neurons at a time, you must be satisfying 3 conditions. Now if I choose a point somewhere, suppose here, then neuron number 1 is satisfied, 2 is satisfied, but 3 is not satisfied. Okay, so if you want to fire all of them, then you have to have point here. If you take this point or any point in this region, then all of them are going to fire. Now can you think, suppose I choose this particular point, suppose B, how many neurons will fire? Anybody, can you answer?
2.
2 neurons.
2 neurons, because this is satisfied, neuron number 3 is satisfied, neuron number 1 is satisfied, neuron number 2 is not satisfied. Okay, so this is the region where we are not interested in. Now let us go to the last one. Suppose I write here neuron 4. What it is doing? It is taking x2 multiplied by -1. You can see here x2 multiplied by this -1. So this will be minus x2, and this -1 multiplied by -3. So +3. Okay. So net 4 is equal to minus x2 plus 3. Now what this implies? it says that your x2 must be less than 3. Okay, x2 must be less than 3, then and then this neuron will fire. Remember, this sum must be more than 0. Okay, so accordingly we have to check what is happening. Suppose this is my 1 here, 2 here, and say 3 here on x2 axis. Then what this neuron is doing, neuron number 4, it is saying that go this side. So if I combine decisions of all the 4 individual neurons, then the common region where all 4 will fire is this one. Is that fine? So if you choose any point within this region, okay, the sum, net sum here will be 4. Do you agree with this? Because if you are in this region, then this will be 1, this will be 1, this is 1, this is 1. All of them will fire. So net here is 4. And 4 minus 3.5 is greater than 0. So this will fire and it will produce +1. So what is the answer to your problem? Find the region in x1, x2 plane where network output is +1. So you have to indicate that this is the region where this circuit will produce +1. So in short, we will say that this is the region which belongs to class 1. Okay, if I redraw, suppose here, so this is x1, this is x2. So this is my neuron number 1, this is neuron number 2, this is 3, and this is 4th one. So this is saying go this side, this is saying go this side, 3rd one is saying go above this line, and 4th one is saying be below this line. Okay, so combiningly this will be my region. If you put your point A in this region, then and then output is +1. So we call this as suppose class 1, and the rest region surrounding this class 1, say whatever is here surrounding this is class 2. Okay, so what this circuit has done, it has divided this space into 2 regions. Region number 1 represents class 1 and region number 2 represents class 2. So what is practical use of this? So this is some theoretical kind of thing. So practically what happens is, suppose your x1 is height and x2 is some length. Suppose these are 2 features of certain problem, and based on these 2 features I want to recognize 2 objects, maybe say a file and maybe say a duster. So for me, file is say class 1 and maybe duster is class 2. Okay, and we have measured height and say length of we can say different objects, that is duster and file, and we have noted down features. So these are called features of those objects. And if this is the region where, say, file belongs, and the rest region is, say, duster. These are some hypothetical problem, but I hope you can understand what is importance of this kind of classification. This is how artificial network learns. So whenever you are presenting different feature vectors, what this neural network is trying to do, it is trying to segregate different objects. So you can see finally how it looks. So this is the region where O5 is equal to 1, and maybe this is 0 if I use TLU or other regions. So we have seen Hebbian, we have seen perceptron, I think Widrow-Hoff is left, then delta, and the others are in pipeline. Okay. So we'll continue our discussion on this learning rules. I have taken intentionally one problem in between so that you will understand what is importance of these networks. Now we will take this Widrow-Hoff, which is very similar to actually delta learning rule. If you remember what is delta learning rule, it is C into D minus O, or if you compare with actually perceptron, it will be better. C into D minus O into X. So this is perceptron. If I write here delta C into D minus O into f dash of net into X. Okay, so these rules are looking very similar. Now if you compare these, so this is delta. So this particular thing in Widrow-Hoff is W transpose X. So this is nothing but net value of neuron. Now if you observe this delta learning rule, there it is called as output. So output is f of net. Okay, if output is f of net, and if I use linear activation function, what is linear activation function? F of net is equal to net. Now if you substitute here linear activation function, what happens? F dash of net with respect to net is 1. Okay, so if I use here delta learning rule, say delta W is C into D minus output into F dash into X, and this output, if I say that I am using linear activation function, say O is f of net and f of net is equal to net, then f dash is 1. So I can write here C into D minus O. What is O now? O is nothing but net. What is f dash? Will be 1 into X. Now this net I can further write as D, say C into D minus, what is net? Net is nothing but W transpose X. into X. So this is just a modified version of, I can say, delta, called as Widrow-Hoff learning rule. So maybe treated as a special case of delta learning rule, and also known as least mean square learning rule. So it was used in networks called as Adeline and Madeline. So Adeline stands for adaptive linear networks, and Madeline stands for multi-adaptive linear networks. Remember that even though I am making the relation between delta and Widrow-Hoff, Widrow-Hoff came into picture earlier than delta learning rule. Okay, so this rule came first, and then this was invented. But there is a relation between these two. What Widrow-Hoff, these two scientists assume that neuron activation function will be linear and based on least mean square, say, error kind of thing, that is gradient based learning is implemented. So this became very popular in those days wherever the problem was handled successfully. So Adeline stands for when I use only one neuron. So this will be the structure x1, x2 up to xn. Then corresponding weights are w1, w2 up to wn. And here there will be a linear activation function. So what is net value here is W transpose X. Okay, I hope you remember these things. I just revise W1 X1 plus W2 X2 plus and so on up to Wn Xn. So this is what is net value going to this neuron. So I can write this in summation form as I equal to 1 to n Wi xi, or I can write same thing in form of vector multiplications as W transpose X. So all these things are same. So throughout this course you remember this thing. Okay. So whenever I write in this form or I write in summation form, if or otherwise I write as multiplication of two vectors, dot product of two vectors, actually they are representing net value of neuron. Now what this Widrow-Hoff is doing is it is saying that output, say output here will be equal to net. That means it is equal to W transpose X. Okay, so that is the only thing they have done. And when I say Madeline, it stands for multi, say, such units in a layer. Say this will be neuron 1 or Adeline 1, this will be 2, this will be 3, and so on up to suppose R. Same input will go to this neuron, this neuron, this neuron, and this neuron. Okay, say this is vector X. It is going to all the neurons. Then what is use of this neuron? Say this will represent class 1, suppose pen. This will represent class 2, maybe duster. Say this is class 3, maybe some eraser, and this class 4 maybe some printer, like that. So I have different categories, and each neuron here is representing one category. Suppose I take only single neuron, then it can produce some output. So I can have a classification of only two objects, either class 1 or class 2. Okay, so when people found that only 2 classes is not sufficient, then what we should do? We should go for multiple neurons, and each neuron will represent one category. So that is how there is advancement from single neuron to, say, many neurons. Okay, so this is about Widrow-Hoff learning rule, which is coming from, say, which is the basis actually for delta learning rule. Then there is a small other rule called as correlation learning rule, which is CDX. So if you remember Hebbian learning rule, which is COX. So C stands for constant, O stands for output of the neuron, and X stands for input. So what is done in correlation? This O is now replaced by D, and where D stands for desired response. Okay, so this is Hebbian, which is unsupervised. So there is no teacher signal, or there is no control over what is expected output in case of Hebbian, whereas in correlation learning rule, this desired response will be provided while training the network. So whenever you provide the desired response, your learning becomes supervised. Okay, so whenever your learning is supervised, you have to provide D signal, that is desired response. So this is also called as a supervised Hebbian learning rule. Okay, so this is a modification, you can say, with Hebbian, where you have provided some desired response, and it is used in memory networks to record data. Okay, so whenever your job is to record data, you will use this correlation. So these rules, they will be coming to you again and again with their respective networks. What we are doing right now is we are just trying to understand what are the basic rules and how to handle these rules. You will find that to compute weight, procedure remains same, but how weights are adopted depends on what rule you are using. Now, which rule you have to use? There are many rules. So which rule? So it depends on what is problem you are tackling with. Okay, what is problem you are handling currently? Depending on that, you have to choose your rule, you have to choose architecture of your circuit, and so on. Okay, so that things we will see later on. Time being, just concentrate on what are types of rules, how they are handling data. So this rule requires, this is a must condition, this rule requires that initial weight of the neuron must be equal to 0. Okay, so this is some requirement of this particular rule. If you go to delta learning rule, perceptron learning rule, Hebbian learning rule, they don't have such requirement. For perceptron and delta learning rule, your initial weight is random. You can assume anything, you start with anything, but eventually your network will learn. Okay, so next topic is what is unsupervised learning, and for that what is our rule, so that we will see in detail next time. So if you have any doubt right now, you can ask me.
Hello, sir. Hello. Hello, sir. Hello.
Yes, anybody? Shall I stop?
Sir, I had doubt.